So historically, I'd say like 100 or more years ago, these scientists have been working long and hard on figuring out why spontaneous processes occur, and it didn't go through, and why, right? And they've developed this whole area, and it's a really useful. I mean, just think of something really complicated, gene transcription, right? Whether you know what the heck it is or not, it's pretty complicated. Very modern research. You can, okay, well, why does it to rule out a lot of stuff? Or what this is more likely to occur, or this is not likely to occur. Weather, metamorphosis, all of these things that happen spontaneously. It's all thermodynamics. You can use thermodynamics to predict and what processes are possible, impossible, and it's really helpful. So we're going to stick with chemistry, the chemical reactions, though. I mean, you don't have to talk about chemical reactions, but thermodynamics is good for a lot of other things. Let's take a look at applying this. So without even looking at a rubber band or a rubber glove at the microscopic level, right? In thermodynamics to do some predictions with what's going on at the microscopic level. Right, Nick? Shall we? Okay. So what's the process we're talking about? We're talking about this guy being stretched. So there's my initial, right? And there's my final. Okay. So delta G for this process must be what? Positive, negative, or zero? What would you say, Juan? Pablo. Here's the initial. All right, there's the final. Delta G for that process must be what? Now, what's the big key about remembering about delta G? There's only one thing to remember about it. Spontaneous. So the question you ask yourself, initial, final. Is that spontaneous? Yeah, I mean, it happens all on its own. You can't stop it, right? You're going to have to stick your hand in there and grab it or something, right? It's definitely spontaneous. So that had better be negative. Okay. Now here's where you need to help me out. Just take this guy and put him on your cheek. Feel the temperature of him, right? And then, to get used to that, and then stretch it and put it on your right? After stretching this rubber band, it feels warm. It feels warm. Okay. So stretching a rubber band, Mariella, must be exo or endo? Exo, because it's giving off heat. Well, if stretching a rubber band is exo, then the contraction, Alexa, of a rubber band must be endo. Yeah. Yes. Do you remember it? That's a good question. Is it the same amount? Well, there might be some funky, weird things going on, but it's going to be really, really close. Because remember those thermodynamic potential energy curves we drew? Right? You start out with the reactants going to products. You can go either way. Right? But yeah, it's the same delta H. Just flip the sign. When you flip a reaction, just flip the. So yeah, they would be. So let's see. So we just said contracting rubber band must be endo. Okay? So contracting a rubber band, contracting rubber band, it's sucking up heat. Delta H for a contracting rubber band must be, Nick, what would you say? Positive, negative, or zero? Positive, yeah, because we just contraction is endo, so it has to be positive. Okay. Therefore, delta F must be what? Well, we're going to have to figure this. Let's do some math here. We said delta G had to be negative because this rubber band spontaneously contracts. Nick said delta H had to be positive. Right? Okay. So looking at the equation and looking at the equation alone, Javier, delta S must be, there's only one way to make the math work out. Must be, I just pick one and put it in. If you pick negative, right? You put in a negative number for this. Negative times a negative is a positive. Positive, positive. That ain't gonna work, right? So you're right. It's got to be negative. You know what I say? Positive. Because a positive times a negative is negative. You add it to a positive number, you can get a negative number. This needs to be huge, right? It needs to be huge. So that means that delta S, the entropy, when you do this, right, start here, end up there, it's increasing or decreasing? Positive. It's increasing. Because delta, remember, it's final minus initial, end up with a big positive number, so final's got to be a lot bigger than the initial. Okay? Big positive number. So that means what then? The energy is more, what do we talk about entropy? If entropy is increasing, what was the idea behind that? Energy is more, is energy more dispersed or is it more concentrated? Dispersed. So when you let go of that rubber band, the energy spreads out more. And just by looking at the equation, that's what you'd be predicting. You have no idea what's going on at the molecular level, but however this energy is distributed, it's spreading out. If you take a look at what's going on at the molecular level,
So is it more spread out in,
exactly. It's got to be more stretched. It's got to be more spread out when it's unstretched. Where's the energy in this thing? All right? These big, long, green things. What makes up rubber? Does anybody know? What are these big things? There's the P. They're just big, long, extremely long molecules. And they're connected by those red lines called, bonds. Is the best word for it. I wish they would call it bonds, but it's polymer jargon, so they call it crosslinks. That's where your energy is, how your energy is distributed. So when this rubber is stretched, look how uniform the energy is distributed, right? It's here, and then it's there, and then it's there, right? But you let the stuff unstretch, and it turns into spaghetti. The energy is distributed all over the place. And that's not even, so we predicted that without even knowing what it looked like at the molecular level. Okay? So how would we answer that last question? Andrew, how do we answer this last question? Upon contraction of rubber band, the energy in the rubber band becomes more dispersed. Exactly. Positive. Okay. Is that okay? Interpretation of free energy. No, it's spread out more. Yeah, it's now it's unstretched. The energy is dispersed all over the place. Yeah, it's really dispersed. Right. Have the thing stretched? I mean, look, it's even getting smaller, right? And the energy's, it's kind of hard to tell. Really, you can only tell by looking at the molecular level, whether it's spread out or uniform. You wouldn't know that unless you or something. Okay. Interpretation of free energy. When delta G for a process is what, then you could use that process, Shelby, to do work. What do you think? She is right. Do you see why? Because only when delta G is less than 0, the process is spontaneous, right? A ball rolling down a hill. That's not spontaneous. If you have a process to do work, right? It hits something and makes it move. But If you have a non-spontaneous process, something that's not natural, you got to put energy in. You have to do work on it to make it happen. You can't use that kind of process to do work. Okay. Do you remember, Jessica Vaughn, how a physicist defined work? It was what times what? Yeah, force times distance. If we take a closer look at this equation, what do the units of work have to be? Joules. Yeah, or kilojoules, whatever your delta G is in. Work is energy. Kind of odd way of thinking about it, but work is energy. It makes sense, though. You eat a Snickers bar. How do you know how much energy is in a Snickers bar? They don't use joules, they use calories. Right? So, yeah, you consume energy, you do work with it. It's just different forms of energy. That's really all work is different forms of energy. But transforming energy from one form to another. But that's kind of for later chemistry class. So let's calculate a thermodynamic equilibrium constant. Vanessa, all equilibrium constants, they're what over what? Product over reactant. The only difference between a thermodynamic equilibrium constant and what we've been doing before, Kc, are the units. It's got to be careful. Okay? And the reason why they're now interested in a thermodynamic equilibrium constant, look down here. There it is. You can get equilibrium constants if you know what the delta G0 is. That's where we're headed with this. But it's kind of a different equilibrium constant, even though it's product over reactant. So let's get started here. Everything we've done so far, Mallory, has been Kc for equilibrium constant. Even gases, everything, they're expressed in units of what? We use brackets, and we said, hey, what units do we use? Where's Mallory? Yeah. What do we use for units when we plug this stuff in? We want to get a number for our equilibrium constant. It's product over reactants, but everything was in units of, anybody help her? Big M, right? Everything is in units of big M, which is what over what? Moles over liters, but it's easier to write big M, okay? So now in thermodynamic equilibrium constant expression, all concentrations are in units of big M. It doesn't change, except, now here's the difference, Adrian. What? Except what? A hint. Here's a hint. Gases. Right? Except gases. Now, what are some units, Victoria, of at? What are the units of pressure that it could be in? Yeah, ATM is what they're going to pick. They could have picked Pascal. They could have picked pounds per square inch. They could have picked millimeters of mercury. They could have picked torr. They just picked ATM. Fine. Okay. So what this is going to come down to is we're going to write big K, and it's going to be products over reactants. But if you ever see a gas, you don't write brackets. You write big P. And then the little subscript is going to be whatever the thing is. Nitrogen, put N2. Okay, that's what we're going to be doing. You'll see that in a little bit. Partial pressure. Jessica Rojas, what was partial pressure? How can we describe it? I don't know if this is going to help. But what's one of the gases in this bag? This sealed bag, what's one of the gases? Oxygen's one of them. Carbon, there's a little carbon dioxide, yeah. A lot of nitrogen, 70-some%. What else could be in there, maybe? Maybe you named pretty much everything. Or there could be some water, right? There's some water vapor in there. But anyway, you add up the individual pressures of all those gases, and you get the total pressure. What's the total pressure going to be close to? 1 atmosphere, right? If we were at sea level and the weather was behaving, it'd be 1 atmosphere. But that's what the partial pressure stuff was. You could say the total pressure, the sum of all the partial pressures, and then whatever they are. Right? So instead of writing A, you write nitrogen. Instead of writing B, you write oxygen. Okay? And then if you wanted to calculate, here's the only other equation we had. This one. What was that called? Jose, what was that equation called? There's an I. The ideal gas law. That's the ideal gas law. Okay. Now the trick to figuring out partial pressures was, okay, we want to calculate it and use the ideal gas law. You just put an A there, whatever gas it is, nitrogen, oxygen, whatever. Now you put that subscript of that gas somewhere else. Matteo, where do you put it? The N. You nailed it. What was the N? It was the mole. That's how you get these A anywhere else? No. Because they're all in the same container. They all have the same temperature. They all use the same gas constant. You're done. So those are the two equations you can use to get partial pressure if you have to. Okay. So you go through all the work to get delta G0. Notice how are you probably going to get delta G0? Yeah, how do you get it? We use, what do we use? Yeah, product minus factor. We're going to use a table. Exactly. That's how we get the delta G. Now, what's the hint that you're supposed to do that? The little zero, the superscript 0. That's the hint saying use the table. Right? Okay, so you go through it's going to be a homework question. And then you got to solve for K. Okay? Now, before we do the math and solve for K, which R would you use? Yeah, R is that gas constant. Number? 0.0821. But we never memorized the unit. But if you did, they were liter atmosphere over mole Kelvin. Those units will not work. You have to use the R that has joules in it. Now, the one that had joules in it was 8.314. Now, I give that stuff to you. You just got to make sure you pick the right one. Okay? 8.314 joules per mole Kelvin. That means T has to be in what unit? Kelvin. And delta G0, now do you remember this? Use the tables, you get delta G0 in what unit? Kilojoules over mole. So, you see how the kilojoules thing isn't going to work. Joules. Otherwise, things are going to get messed up here. Anyway, so let's say you do all that. You plug in, you get the right R, you get the right delta G0, you get it in units of joules per mole. Okay? How do you solve for the K? Ray, what would you do first? I would leave the L and K part alone. Worry about that later. Just move the R and the T over. Let's start with that. Delta G, divide up both sides of RT. Okay. Before we had an equation with LOG in it. And we got rid of it by taking both sides to what? Raising them both sides to not E. LOG, we raised both sides to 10. Right? We raised both sides to the 10 power to get rid of LOG. Now we have LN, raise both sides to E. Raise both sides to little e. So it's going to look like this. Little e, negative delta G0 over RT, little e, ln k. Now since little e and ln are inverse functions, they're gone. That's how we're going to get our K. Okay? So the K is going to be negative delta G0 over RT, e raised to that power. This is because this is the equation I give you. This is what's given on quizzes, homework. Know how to go from here to there. Okay? You have to know how to go from one to the other. Oh, remind ourselves, which R do we have? The 8.314. And the delta G needs to be in units of joules. Okay. What's the difference, Jasmine, between delta G and delta G0? The what? Yeah, what does that mean? 25 degrees Celsius. This one is at 25 degrees Celsius and 1 atmosphere. They call those what? They call those what conditions? Standard. Right? STP. Standard temperature and pressure. That's what the little zero means. That means you can use the table. Delta G just means you're not at standard conditions, so you can't use the table. Okay. So that's where we're at. So you mess with the temperature at least. Hey, you're not at 25 degrees Celsius. You know, whatever temperature you want. Right? That's what the T means. Whatever the temperature is, plug it in right here. Oh, but make sure the units are what? Kelvin. Make sure they're in Kelvin. And then you get this guy and this one. Now, how are you going to get these two? Tables. And how do you know that? Because of the little zero. Exactly. All right? You see the superscript zeros on them, they're STP. So, not so bad. So we're ready for the homework already. Give the expression for the thermodynamic equilibrium constant for the following reaction. Amanda, what's the symbol for the thermodynamic equilibrium constant? What was the symbol for it? Anybody help her? What was it? Big K. All right. And I say be anal about your notation, because be particular about it. It really guides you. Okay? If you remember, oh yeah, that's big K. So I got to be careful. It's the expression. So that means it's just what over what? Products over reactants. So what would you write, Mariella? Mg2 plus, but in what? Concentration. Concentration is bracket. Good. Keep going. OH minus squared. Oh, careful. Over 1. Good. Alexa, we're giving the, again, expression for the thermodynamic equilibrium constant. So the same thing. Now what would you write? H3OH, but whoa. What's wrong with writing the bracket? It's a gas. So we can't use brackets, we have to use big P. So Alexa, big P, CH3OH is what it's got to look like. Nick, what would you put on the bottom? Yeah. Yeah. What do you do with the 2? Yeah. Stoichiometric coefficients always become powers. Why doesn't this thing write anymore? Strange. Look at that. That never happened before. Wow. All right. Okay. So you have to square it. Make sure you put a 2 up there. Wow. Yeah, make sure you you're squaring the P. Strange. Okay. Let's try something. I have to open it up again. See if there's so much stuff to write. 32. All right, let's see if it works. Oh, what I did. Okay, where are we? We are 60? Oh, we finished. Yeah, we did. Okay. We're here. Thank you, sir. What is the standard free energy change at 25 for the following reaction? Okay. Andrew, what do we do to get this? What would be the game plan for something like this? Use the table. He's right. How does he know to use the table? Yeah. There. And they also said standard. Okay. So delta G0. Product minus reactant. Oh, I forgot to bring my book. Too good. All right. Andrew got, so he doesn't have to look this stuff up. Oh, shit. The table's all nice. Look at this. Now, you got to make sure we give this back to her. Let's pass to these bums in the back. Okay. So, look up HBr, and so it should be with the bromine stuff. And it needs to be HBr, it needs to be gas. You see it in there? Who did I give it to? Thank you, Jasmine. HBr needs to be in the bromine compounds there. And we need the delta G for it. Negative 53.50. Okay. Oh, thank you, sir. Times 2. Jasmine, this way. Now we need Br2 liquid. Those bromines. Br2 liquid. The delta G for it. 0. How about the H2 gas? The delta G for it. It's 0. Okay. So, what are the units for delta G0 in our tables there, Jasmine? All over moles. So 2 times should be like negative 107? Yeah. Okay. We got it. What's the value for the thermodynamic equilibrium constant? All right. Oh, we don't need that yet, do we, Nick? Nick, hang on to it, though. Let's ask somebody else. Javier, how are we going to get the thermodynamic equilibrium constant? What equations are we going to be messing with? You see something in there? I don't know. Just say it. I can't hear it. Yeah, and this is delta G0, right? Okay, so there's our equation. Remember, you have to know how to manipulate it. And when you manipulate it, we ended up with big K equals, wasn't it E? The negative delta G0 over RT. You remember that, right? Okay. So, can we just plug and chug? No. Yeah, this guy needs to be in what unit?
Joules over mole.
Joules over mole. Okay. So now, which way do you move the decimal point? Make it bigger or smaller? Make it bigger, right? Because kilo's 1,000 joules. Just one of them. So it's going to be negative 107, 1, 2, 3. All right? And if you're not sure, you can always just put 10 to the third in per kilo. That's what it means. Okay, now we can plug stuff in. So big K, and E, negative delta G0, negative 107,000.
Is it negative?
Oh, yeah, I forgot my negative. Thank you, sir. Okay. Divide it by RT. The R I'm supposed to use is 8.314. And my T is what? Needs to be in Kelvin. Add 2 things. What's the temperature where we're at? 25. It's kind of right here. So 298. Okay, plug that stuff in and see what you get. See if you know how to do the E button. I got about 5.7 times 10 to the 18th. Okay, so what I did is I just forgot about the negatives because I'm going to cancel out, right? So the 107,000, divide it by 8.314, divide it by the 298, and then hit equal, and then you got to do shift e to the x. And it should work out. Now, if you have a different, one of these big calculators that you didn't loan out, someone else has to help you here. Anybody having trouble with it?
You forgot to put the data before that. There's 2 negatives. I got 1.
Alexa, did you get it? Oh, you have a big calculator. Mandy, you figured it out? Try. All right.
And divided by 298.
Pablo, what's the free energy change at 1,000 degrees Celsius for the following reaction? What equation are we going to use to start us off on this thing? What was the equation?
The E1, delta G equals negative RT. Yeah.
This one?
No, because it doesn't have to do on the delta. No, but not the 0 though.
This isn't going to help us. We don't even know what K is.
So when you do, all you use the.
And they want to know what is the free energy change. Notice this, because we just copied that, that's one of our equations. This is not that.
It's the other one then with the G times H.
There you go. Delta G with the T on the bottom equals, keep going. There, that one would work, right? Because they gave us the reaction. They told us to use the table so we can get these two and just make sure we plug in the right temperature. What are we going to plug in for temperature? 1,000 plus 273. All right, so let's see if we can get these guys. We need delta H. We need delta F. And we need products minus reactants. So I think, who did we give that Vanessa's table to? Products minus reactants. We have HBr here. And then we need H2 and Br2. Okay, I think we gave the table. Nick, don't you have the table? Yeah, okay. So look up HBr, gas, and we need the delta H. Should be with the bromine. Negative 36.44. Oh, thank you, times 2. Okay, how about the delta F for HBr, gas? $198.6 times 2. All right. And now we need H2 gas, and it's delta H. 0. H2 gas, we need its delta F. 138, 130.6. Now we need bromines. Br2 delta H needs to be liquid. Zero. And we need, I couldn't hear. Br2 liquid delta F. 152.2. Okay. Now, before we let you go, Nick, what are the units for the delta H in the table? Kilojoules over moles. And in the delta F? Okay. All right, so let's see if we can get these numbers here. So it should be about a negative 72.8. And those are the two numbers I got. Negative 72.8 and 114.4. So if we're going to plug them into this equation, what should we do before we just start plugging and chugging? Yeah, let's convert the delta S into kilojoules. Because I think the book likes kilojoules for stuff, so let's do that. We don't have to. We can convert delta H to joules, but I like Matt's idea. We have delta S, convert to kilojoules, make the number smaller or bigger? Make it smaller, 0.114. So we'll have the negative 72.8 joules per mole for our delta F, delta H, minus 1273 Kelvin, and then 0.1144 joules per mole Kelvin. Okay. Oh, sorry. Let's see, our kelvins are gone. So we end up with kilojoules per mole and kilojoules per mole. Should work. Anybody get an answer? Did you get like negative 218? Okay, good deal. Right here? Products minus reactants. We're We're about out of time. This last question is about the same as one we just did. But have a good break. Come by and ask some questions. Oh, I need my little rubber fingers back.
I'm going home sick. Yeah.